Okay, let's move to the constraints. We have introduced the constraint on relationships, and here we want to introduce more constraints. What is a constraint? Formally, constraint denotes an assertion about the database that must be true all the time. So the constraint can be very different. We have different constraints in database systems, and they can be very different from each other. The constraint can be part of the database schema, and it will be very important in the database design. According to our previous lecture, we remind you every time whenever you join a relationship, ask yourself what is the constraint on the relationship. One-to-one, one-to-many, or many-to-many. Here we will cover more constraints. The first one will be keys. Generally, keys will be on some entities. So for example, for a person as an entity, we can use some attributes like a social security number as a key for it, for a person entity, because this social security number can uniquely identify a person. Then what is a key? We will introduce the key, the definition later, because it will be very complicated. So far you can understand in this way. So the key can be one or a combination of multiple attributes that together will uniquely identify some data tuples. For example, the SSN will be a key for a person. Your FSU ID will be a key for a student in FSU. Right. Besides the key, we also have some other constraints, like a single value constraint. For example, in the real world, a person can have only one father. We should avoid inserting multiple fathers for a person, right? Another important constraint we introduce here is called referential integrated constraint. So it denotes some entity should exist whenever we reference it. So for example, if we work for a company, in other words, we create one relation between employee and a company. Once we add some relationship between you and a company, then this company should exist in the database system. We cannot connect you with some company non-exist. We cannot connect you with some non-existing companies. Also, we have some domain constraint. A person's age should be between 0 and 150. We cannot have a person's age which is -10, something like this, right? We can also have some other constraints. For example, we can set a limit for the enrolled number of students in a course, like 60 students. So constraint can be very important. It is also one part in a database design. Therefore, when you are drawing your ER diagram, besides the constraint we learned for the relationships, you should also ask yourself, does this ER model has any other constraint or not? You may also wonder why we should have this constraint. The main reason is because the real world can be very complicated, and the information or data we can get from the real world has different semantic meanings. And when we borrow the real world or applications with database systems, we should be able to keep as much this semantic information as possible. Therefore, with the constraints, we can give more semantics to the database design. For the keys, it will also allow us to refer to some entities with some simple attributes. Like I can use the SSN refer to a person. Instead of describing all the attributes for a person, right? We can just use his SSN in reference to the person. It will be much more efficient in the storage as well as data lookup. So that in reference to a person, besides SSN, can we have any other keys? Someone may say we can use a name as a key. However, in the real world, maybe the name is not enough. So at the bottom, we show an example about Michael Jordan. When we talk about Michael Jordan, I think for you, most of you will assume we are talking about the first person. The basketball player is very famous, right? However, in the near future, if you plan to go to a graduate school and do research on machine learning or on data mining, then when we are talking about Michael Jordan, it is high likely that we are talking about the second person. He is a professor from UC Berkeley. So, in other words, in referencing to a person, maybe the name alone is not enough, and we can combine the name as well as his employer together. This can serve a key for the person as well. Therefore, you can see for the key in referencing to entity, we have different options. besides SSN, we can also use the name combining employer as another key as well. Of course, you can also find some other keys like passport number. It's a different key. So you can see we have different choices of keys. We will mention this later as we are talking about relational algebra in the near future. So when we draw a ER diagram, we need to highlight its key for the entities. So for example, in this page, we show two entities. The first one is about product. The product entity has three attributes: price, name, and a category. For the product, maybe the name alone is not enough to serve as a key to differentiate different products. Therefore, we propose to combine them with category that together can serve as a key for products. To highlight the other keys, so we can underline them and a category together in the diagram. So for the person, according to the previous page, we have different choices to define a key for the person entity. Besides the SSN, we can also use the name with address that together can also serve as a key for a person as well. However, for the ER diagram, we have no formal way to specify multiple keys. Therefore, we have to choose one key for the person entity. Here we choose user SSN and we underline it to highlight it as the key. If you don't like the SSN, you can also remove the underline here and also add an underline to name with address. It together can also serve as a key for a person. So there will be different choices and you can decide which one you like or which one works better for you. So every entity must have a key. Key is very important in the entities. So whenever you draw an entity in the ER diagram, ask yourself what is the key for the entity. You may wonder why a key is very important. The main reason is because we need to store the data in our database tables. Let's assume we translate the ER diagram into relations and further create some tables to store the data. Now for a person, when we store all the person data into the tables, how can we locate one specific person meeting our search requirements? We need to have a key in reference to a specific person, right? This key can serve as an ID of these data tuples or pairs in our tables. So the key is very important. As we mentioned, a key can consist of more than one attribute. Sometimes one attribute is enough. However, sometimes we need to use multiple attributes. And the largest key we can create for an entity will be the combination of all the attributes of an entity. It is also allowed, right? We can use all attributes of an entity serve as a key. They can also uniquely identify a data tuple in our tables. So in other words, there can be more than one key for an entity set, and among all these candidate keys, one key will be designed as a primary key. Therefore, besides the constraint on the relationships, you also need to pay attention to the keys on the entities. Whenever you draw an entity, ask yourself what is the key on this entity. Besides the keys, we also need to introduce another very important constraint here. It's called the referential integrated constraint. This is mainly used for in referencing to entities. When we are referring to an entity, this entity must exist and also contains only one single value in a given row. So the physical meaning of this constraint comes into two folds. The first one is the entity we're referring to should exist. The second one is that there should only exist one single of this entity in our tables. It is very important. In our database table designs, in most of cases, we use this constraint for the relationships. We may refer to some entities via these relationships among the entities. For example, when we are referring to the complaint we are working for, so from the employee via this works for relationship, we can refer to this complaint, right? So we need to ensure this complaint exists in our tables, and also there exists only one single complaint, and that we are referring to. And you may also compare this constraint with something we learned from the programming course. If you still remember, in the programming course, we have a concept it's called dangling point in C++ or C. In sometimes we may create a variable in referring to some memory block or memory space. However, by mistake, we can delete the space by some other code. And when we further referring to this memory space via the existing variables or pointers, we may get some garbage information. And formally we name these kinds of variables or pointers as this dangling point. Technically, point is very bad, and it may create lots of problems because as the program runs and goes by via long time, it may consume lots of memory space and may create lots of problems for the software. And in our database design, we want to avoid similar cases, and we want to ensure that whenever we refer to some entities, it must exist and also contains only one single of these tuples in our tables. Therefore, we can introduce this referential integrated constraint. Okay, so how can we represent this referential integrated constraint in the ER diagrams? In this page, we show you with an example. So we can focus on the first part. Let's assume we have two entities. The first one is a product, the second one is a component. Between them, we have a relationship, the max. It means the component makes this product. Given a product via this max relationship, we can refer to some components. If we have some special requirements in the reference, like we need to make sure this component exists and also only contains one single component makes this product. If so, then we can add one rounded arrow pointing to the component, as shown here. So what does this diagram mean? When we have a diagram like this, we can read the diagram into two perspectives. The first perspective will be, if I know a product, given a product, I can find one single component that makes this product. In addition, this component must exist in our database tables. So from our product, we're referring to the component makes it. This component should exist only one single component. Also, this component must exist in our tables. This is the physical meaning of the diagram like this, with the rounded arrow pointing to the components. And you may also want to compare this referential integrated constraint with some constraint we have known already, like the kinetic constraint on relationships. Before we have some diagram like this, product component, we have max as well, and we have this arrow pointing to components. This arrow is different from this rounded arrow we show here. It's different. We have introduced this physical meaning for the diagram like this in the bottom already. It means if I know a component, then I can only find one single component that makes the product. It means a magnitude 1, right? So you should be able to differentiate these two constraints on relationship max. Also how to draw these arrows in different constraints.